Okay, welcome back everyone, and welcome to this potentially the last lecture of this series. And we are certainly in the end game now. Yes, I've been waiting for 18 lectures to say this. But we will still have quite some concept to go through, and this lesson will by no means be easy. There are quite some mind-bending new things, new concepts, a couple probably around 5 that I can count, new things that you still need to learn from here. So it's going to be packed full, and we have lots to do. But yeah, I think this is also one of the more interesting, some of the more interesting topics to go through as well. So just sit in there, because if you've sat through so many lectures already, well, you're committed. So we don't relax just yet, but we will end with some of a very impactful kind of lesson over here. But we'll really be able to wrap up our whole journey, right? Because remember, we begin motivating. We have one goal, essentially, in 3A, is to analyze how things move. All right. So I think with this last lesson over here, we'll be able to conclude that and understand the whole basic model, a basic way. How do we describe? How do we measure motion? Let me start over. How do we measure motion first? And no, that's the right way. How do we first describe it in a very precise and scientific way? And then how do we measure these things? And how do we make predictions with these things? And also understand what are the things that causes motion? And in our theory that Newton set up, or one of the first person who set up all these theories, is saying force is the origin of things. And we also realize there is the energy approach, which is a different way of looking at things and say the difference in energies causes. For example, if this guy went from here to here, the reason why it speeds up is because there's a difference in potential energy due to the Earth, difference in gravitational potential energy, and it has more energy here and less energy here because of the we invent the law of conservation of energy, and you understand that well, there's some energy loss in this process, so there must be some other energy gain. Why does it go to kinetic energy? That's why does it? Why didn't, if I let go? It's actually a good question, right? If I let go over here, another thing that could happen and satisfy the law of conservation of energy is if I let go, it just heats up, or it moves down over here. So sorry, I should say it moved from a high potential to low potential, so it lost energy, but it didn't gain any speed. It just heats up. Is that possible? It satisfies the law of conservation of energy, but that's a deeper question. So we're not too much in the business of asking why in some sense. That is much more in the realm of theoretical physics, beyond the thing we can discuss, but at least we are able to explain how, and at least be able to predict the speed that it will. All right, so given that it does fall to here, we can predict, and the fact that you're told that it transforms into kinetic energy, you can predict it. Anyway, we wrap up this whole journey that we have with asking originally, right, why and how things move, and we will conclude with these two lectures on a very specific type of motion is going to be why. So we have essentially talked about this already, about how it moves in a linear way, but now we are concluded by asking why and how things move, not necessarily move, but why and how things rotate. Okay, so this is how we'll end this whole series. And believe it or not, you will have all the tools ready to sort of take on quote unquote more realistic examples than just box slope sliding down a slope. But hopefully you sort of see, if you, with a little bit of imagination, a little bit of creativity, you can see there are good real everyday applications as well. So if you want to park a car on a slope, now you know exactly what coefficient of friction your tire better have with the floor if you don't want to come back in an hour later and find your car all the way down in the sea. So you can see, you know, if you need to deliver any medicine to someone on a high story building, you know how much velocity you launch it with. With a little bit of creativity, you can think of good applications as well. But anyway, this is really all the basic tools that you need to be able to take it on and into 3B and 3C and look at more, let's say, varied and diverse examples, right? All right, so back over here, right? So how, why and how things rotate. So we now have we now actually in the previous lesson already learned how to describe rotations, okay? We learned how to describe that, and now we just need to go and figure out the cause. What do I mean, right? So we know how to describe it just like how we did with kinematics or linear motion. We know how to describe things. Things will, when they rotate, the key kinematics quantity, although this is rotational kinematics quantities, right? Quantity, remember, is a measurable thing in science. We call it a quantity, is theta, right? And if it rotates, it better change with time. And we can talk about the speed of the rotation. This is the rotational speed, right? It's defined as rate of change of theta. How fast does this function, right? Theta as a function of time changes with time. How fast does it do that? And the acceleration, which is how fast does, not a circular definition there, almost, how fast does the speed as a function of time changes with time. You can talk about an average, in which case you just change that into delta. That will be average, and this is instantaneous. All right, so we know how to describe. These are sort of the key players, right? Just like in SUVAT, those are the key players in it. Now, what causes these things to rotate? This is the big question, right? And we sort of already have a little bit of intuition, a little bit of sense as we have motivated, right? If I have a ball over here, again, this is assume I have a sphere, right, floating in space. So no gravity, no friction, no table. All right, this is in space. All right, so just floating in space. All right, now I'm going to give it a kick, right, or a push. So where I push it now matters. We learned about the idea of center of mass, and if it's slightly more irregular, or if it's made of composite objects, how do you calculate where the center of mass is? So we know what the center of mass means. So let's say that's the center of mass, and we define, in fact, center of mass is defined as the position. It's defined as the position where when you apply a force along towards the center of mass, this object will just move in a linear way without rotation. So that is essentially, in essence, its definition. That's the position where when you apply a force there. Okay, so what causes rotation? I think we already have an elementary answer is, well, now let me take this and shift it away from the center of mass. Now we will be able, again, it's almost by definition, right? If I apply a force over here, so what will happen, right, is now this, the force, when I apply it here, let's say it's a contact force, I'm going to punch it. So this particle of the ball is going to feel a force. Yeah, let's draw it that way. However, it's not, as you can see, this vector does not go through the center of mass. Maybe I should draw a separate diagram. You know what? Yeah, let's stick with, yeah, let's keep that in case you're copying notes. So if I punch it over here, this is the point of contact, and that's the force, right? So that's the force. And you see the force vector actually goes through the center of mass, whereas example number 2, if I punch it slightly off center, then this is the place of contact. And if I punch it in this direction, so that this particle experiences a force this way, you see here, it's displaced away a little bit. There's a displacement away from the center of mass. What will it do? That will cause rotation. Okay, so now I have a question for you, right? Let's, instead of a sphere, which is slightly curvy and a little bit annoying to analyze, let's have this as just a rectangular rod or something like this, right? So that's the center of mass. Let's assume it's nice and simple. All right, so if I apply a force here, okay, so this part of the diagram, notice this is the only 2 lectures in the whole course, lecture 17 and 18, where when I draw free body diagram, it's not everything from the center of mass, okay? And in fact, so this is the sort of the general rule is, if you don't care about rotation, draw everything from the center of mass, because that's you're assuming you're just calculating everything as and worrying about its linear motion and not its intrinsic rotation. Okay, the only time you don't draw it away it is from the center of mass is if you care about rotation. Okay, so having said that, right, this is the point of contact. So I'm going to draw this. In some sense, I'm drawing the free body diagram of this particular particle. Yeah, right. So that's another way of thinking about it. So all right, so that if I push, right, so that's the force, and it's not going to rotate. That we understand. All right, F1 will not cause a rotation. But if I apply it here, should I use a different color? Yeah, let me use a different color. All right, so if I apply it here with F2, so like this. All right, so we understand if the center of mass is here, all right, so it will probably rotate this way. And if I apply it slightly even further off center and apply a force on here, so this particle will experience a force F3 like this, okay? Now, assume all of them have the same magnitude, okay? So F1 equals to F2 equals to F3, okay? Notice no vector sign means magnitude. So apply it with all the three color force one at a time with same magnitude but different location. Which one will cause the most rotation? Well, we know this guy, the black one, will not cause any rotation. Will it make a difference if I cause the same, if I apply the same force over here? What do you think? All right. So you kind of have a sense already when you need to open the door, right? When you open the door, so let's look at a top view of, let's say that's a door. You're gonna open it downwards. That's the hinge, right? Are you going to push a door? Let's say when you push a door, that's the hinge, right? When you're walking through here, this is the top view. Are you going to push it towards the edge or towards the hinge over here? You realize if you apply the same force, it's much more effective to cause the rotation to cause this guy, right? Theta as a function of t. Now we know how to describe rotation. So that's the benefit of learning physics. You can talk about things in terms of variables that no one know what you mean. So yeah, you can push it when you push it with the same force. You have a much more harder time to do it here than here, right? You want to push it away from the hinge. Okay, so this is your intuition. So you probably guessed it already. The red one will have the most effectiveness to cause the rotation. Now why? And how do we analyze this? All right, so what we are going to find out is we are going to learn three new formulas today. I can even summarize it here. And it is exactly the same as the ones you've learned before, but it's for rotation, okay? So before we've learned a rule called Newton's second law, F equals ma, but as you now know, it's better to write it this way. And I'm considering, should I write it the other way? You know what, just for today, let's not talk about this, but I'll just sneak this in. I'll write it this way, just because I want a sort of a symmetry over here. Oops, I meant P. So these are three key formulas, three key concepts for linear motion: force, momentum, and kinetic energy. Right? You agree these are key quantities, and they have an angular counterpart. Okay, the angular counterpart is this. Okay, this is going to be the Newton's second law for rotations. All right, so the A becomes alpha. All right, M is the inertia for linear motion, and this is the moment of inertia, which is the inertia for rotational motion. And now there's this Greek letter tau, right? But the Greek letter is called tau, but the physical quantity is called torque. Okay, so torque plays the role of force. In some sense, torque is a rotational force, or the force that causes rotation. Okay, angular acceleration, you can write down your own notes. I'm just going to save a little time and ink over here. Write down your own notes to remind yourself. That's angular acceleration, moment of inertia, right? Linear acceleration, in some sense, well, mass, but in some sense, linear inertia. And this is, what's that again? Linear momentum, right? Mass and velocity. So can you guess how this would get promoted into, what is the analog, what is the counterpart of in the rotational world, right? This is the linear world, this is the rotational world. Well, M is going to be replaced by I, because I measures how difficult something is going to rotate, M measures how difficult something is going to move in a straight line. V is going to be replaced by, what is it? Omega. And P, we need a new symbol, and it's going to be L. Okay, this is one of the few that for the rotational world that usually things that are in Greek letter, but don't ask them. Yeah, don't go down the rabbit hole of asking why a symbol is a certain way. I have no idea. But yeah, can you guess what that's called? If this is called linear momentum, this is going to call, you know, physicists are not the most creative people. This is called the angular momentum. This is something we'll introduce today. Angular momentum. This is linear momentum. And finally, for this, the last one, you can almost guess as well what the mass is going to replace by I. So this time I want a rotational kinetic energy. This is a linear kinetic energy and the rotational one. So the M is going to be promoted to a, or be changed into a, translated into I. The V is going to translate into the omega. 1/2 is still going to be there. And that's the rotational kinetic energy. And really physicists are getting out of ideas. So we don't even have a special symbol for the rotational kinetic energy. We just call it kinetic subscript rot or rotation. This one, you can call it K linear or K translational, right, or translation. Okay, so this is called the translational kinetic energy. This is called the rotational kinetic energy. And depending on how lazy or unlazy you are, you want to write out how much words you want to write out. But yeah, so these are the 3 key formula we will learn. Now, you also, just a little, right, a little preview as well. You also understand we have an upgraded version of Newton's second law where this is dp dt, because this is mv. If m doesn't change, it just reproduces ma. But if m does change, this has to be inside. You have to take the derivative altogether because, yeah, if m is a function of time as well, which usually they aren't, but sometimes there is. For example, in the rocket examples in the textbook, you can see the rocket is basically ejecting mass, and when mass changes, you can provide a force. Okay, yeah. I think I didn't discuss that in detail in lecture, but you should have seen that in the textbook, like ddt, right, of mv. If I want the rocket to go at a constant speed, how are they going to do it? Well, you need a thrust, right? Yeah. So what's happening is, if I wanted to go at a constant speed, if you wanted to accelerate, so the speed also changes, then it has to be inside the derivative. But let's do the physicist thing, right? We'll solve one thing at a time. Let's say v does not change, so you pull that out. So I have dm dt times v. So assume v is a constant, but m changes with time. So m is a function of time. All right. So you now know if you want to, let's say, achieve a certain force with to go at a certain speed, you need to eject how much mass, or put it another way, right? So what's the unit over here? It's kilograms per second, right? So if you eject out 5 kilograms per second, let's say if you eject out 5 kilograms per second and you're moving at a speed of 2 meters per second, right? Then you will experience a force of 10 newtons. Okay, so that's one way you can experience a force, right? Like that. So we know that this is the upgraded version of Newton's second law, which means there is also the sort of upgraded version of the rotation version. Again, it looks a bit awkward to memorize, but the trick really is just to translate them variable by variable. Okay, so know that torque is the rotational counterpart to force. I is the rotational counterpart to this, and etc. Right? So here you have dl dt as well, like that. Okay. One more thing we will address is these things are actually vectors. Yeah, let me put it in a different color just to emphasize that. And right? So these things are vectors. Mass is not, but that's fine. This is a scalar because a vector square, whenever you see vector square, it really just means this magnitude square, okay? So how do these guys work is we need these guys to be a vector as well, right? So this remains as a scalar. Energy, that's why energy is nice, right? Energy, that's kind of the motivation of working with energy in the first place. So we need to understand what does the direction of this means. And we talked a little bit about omega being a vector, right? So omega is how much angle it changes per unit time, right? So where does the direction come from is we define, all right, the magnet. So if I tell you, hey, that's the omega vector, it basically says, all right, let me measure how long this is. That will tell me the rotational speed. And now the vector also cleverly, quite genius, if I may say so, it quite geniusly also tells me which way, which is the orientation it's rotating. It's rotating using your right hand, point your thumb around the direction of the vector, right? Your fingers will tell you the plane of rotation. So you can draw a 90 degrees plane towards the meeting the vector like this, and it's basically moving in the right hand direction, what we call the right hand direction, like that. I don't know if it shows up well on camera, hopefully. Yeah, let's say this is the vector. So you do this, so it's going this way. If the vector is pointing into the board, I can't really put this on the other side, but imagine the omega vector is pointing into the board like this, then you use your right hand again, wrap it around the omega vector, and you can now tell that the object's rotating in basically from this angle, right, clockwise. Okay, and how fast clockwise? Well, look at the magnitude of this vector. So it's a clever way to do that, and we'll talk about all that. Okay, so the very first video we'll look at first is the one more new technique to deal with vector multiplications, and it's the one that I've sort of hinted all along. It's called the vector cross product. So this will also finally complete your study about vector mathematics. Okay, I motivated, sort of hinted from the first day that there's different ways to multiply arrows, and you're finally going to learn all the different ways. And this is the final way we're going to talk about that. All right, let's go.